A lot of times you're going to see me do is I will draw a square and say this is probably going to it's probably a good idea to put it on the sheet. So let's take something that's very easy example to start with. If given, if given midpoint. So let me write out how I would go about doing this. Let me explain how I would write it first before you guys get it, so that we get the idea of how this flows. What do you guys know about a midpoint? What does it do?
It's the point between two.
That's something that happens. What's created? Two same, equal, congruent segments, correct? Okay. So here's what I would do. If you're given a midpoint, what you're going to do is state some segment is congruent to some other segment. What those letters are going to be is totally, I don't know. You won't know until you read the problem. Because each time you can say X is midpoint of AB, C is midpoint of EF. Behind you. It could be any of those. So I try to write this out in terms of a very, very generic idea. So if I start with the idea that I have, if I'm given midpoint, well, what do? Well, I say that some segment is equal to, or congruent to some other segment. So here's what it would look like in terms of an example. Oops. A lot of times what I'll do is in my progression sheet, since I'm trying to make sure I have a little bit of space, is I'm going to do an example of what it would look like in a proof of how it would be written out. So I would say maybe given C is midpoint of AB, and that is given. This is just an example. C is midpoint of AB. Well, if C is the midpoint of AB, what two segments would be created? Yeah, CA and good. So what you would then say is AC is congruent to CB. And what do you think the reason is? Think about what we just used. We used the definition of a midpoint. Your reason is definition midpoint. And that's kind of how things look. Now also, I would probably do this as well. A, C, B. To remind myself of what it looks like. So not only am I writing down, if I'm given a midpoint, what does that mean? Well, it means segments congruent to segment. I also wrote down an example of what it would look like in a two-column proof. And I also drew a diagram. Those three little bits of information we can put on here for every single definition and theorem that we use. Which means every time we have a proof, you can never say, I don't know what to do. I don't know where to start. Because where does it tell you to start? If you're given this, what do you say? Segment congruent segment. Why? Definition of a midpoint. And you go on from there. Does that kind of make sense of how the progression is kind of, what this allows us to be able to do, it takes away some of the scariness of a proof. Does that make a little bit of sense? As we build this, we're going to have, we'll probably use all of these squares, okay? I always have spares of these things in case you run out of space and whatnot like that, but I cannot lie that this is such a huge, important thing to use. Yes, sir?
Every time I hear CA, it's the dockyard, or something before comes a dockyard number, like CA.
Let's go back to the.
Logic.
Yeah.
So that's
You're right.
like
It was-
39.
Yep. You're right. Irrelevant. It's okay. Thank you though.
Yeah.
So let's look at another one. So we've got midpoint. What's another thing that looks a lot like a midpoint? An angle bisector. Wait. How about we do segment bisector first? Because isn't segment bisector the exact same thing as a midpoint? Well, what's the only different thing? You just use segment bisector instead of midpoint. Let's do that one first, and then we'll do angle bisector. Okay? So we'll do another square.
And Mr. Murphy, does it matter if we're gonna go across?
Not at
or
all.
down?
Not at all.
Right.
Not at all. So let's do this one. We'll say if given segment bisector.
Should we write
Any-
it down?
Yes.
Okay.
Yes, let me go back to midpoint then,
Yeah.
sorry. Actually, I thought you guys were writing that down after I explained how it should look. So, you're right, I did that. Correct. Yep. Oh, I'm gonna have a long conversation.
I can't wait to
It's
give
gonna
you.
be great. It's gonna be great. Hey, what does a segment bisector do? What does it create?
Two
Equal
Yeah.
all sides.
So then we're gonna state, again, same basic idea, some segment is gonna be congruent to some other segment. Now, it is possible that we can have congruent or we can have equal. Bless you. Bless you. What happens a lot of times is, depending upon the style problem, we're going to replace congruent with equality or replace equality with congruency. Sometimes we have to switch between the two depending upon what it's asking us to do. That's down the road, but I just want you guys to understand that eventually, when we say that we have two equal segments, that means they are equal in length, which means we can then say that they are congruent. Or if they are congruent, we can also say that they are equal in length, they're equal in measure. Does that make a little bit of sense? It's a subtle nuance that's within geometry that is, again, back to the vocabulary of it. So as we get through it, you'll start to see again more and more.
Could you say that the equal is like a measurement?
Yes,
Okay.
that's a great way of thinking of it. Yeah, I didn't think of that. It equals like a measurement, guys.
It's like a number, so.
Yeah. SMRT. So here's our example. So we'll say that X is a segment bisector of AB. Just make something up. And that's given. Now remember, a segment bisector can be a point, a line, a ray, another segment. It can be anything. I just wrote X because it was a smaller amount of letters. If X is a segment bisector of AB, what are the two segments going to be then? Just by using the definition. AX and XB, yeah. So then therefore I could say that AX is congruent to XB. And the reason? Well, what definition are we using? Segment bisector. What's going to happen a lot of times, guys, is that whenever you have a given statement that has a definition, the very next thing you're going to do is use that definition. That's how proofs work. They're setting you up to utilize the definitions and theorems and things like that within geometry. So now, a little diagram of that would look like, same basic idea. And I just know that those two things are congruent to one another because there's a point. And that's what it would look like. Okay?
Instead of the points, to actually put like a line segment, does it matter?
It doesn't matter. Yeah, it really, I mean, do you guys want to write it as a line segment? I mean, it doesn't matter. I mean, just remember, a segment bisector can be a point, a line, ray, it can be anything. I just wrote that down because that's what I thought of right away. Yes, sir. I know it's broken. Okay. We okay on that one? Let's look at an angle bisector. What do you think an angle bisector does? It bisects a circle. If given an angle bisector. If you're given an angle bisector, what's created?
Two angles.
What about those two angles?
It's two angles that bisect each other.
The two angles aren't bisect each other. A larger angle has been bisected into two angles, but what do you know about those two angles?
Oh, they equal one.
They're equal. So then, what do you think you would state then? With segment bisectors and midpoints, we said segment congruent. Angle congruent to angle. Because what you're saying there isn't wrong, like angle 1 equal to angle 2 or whatever, but we don't know what that angle is. Is it an angle 1? Is it an angle 2? Let's just say there's two angles that are congruent. So the easiest, the most generic thing to say then is some angle is congruent to some other angle. And then in our definitions then, in our example, we could write it out in terms of some letters then. But this is a very, very generic way of writing it. That we don't have to worry about, oh, is it always going to be angle 1? No, we don't know that. So that's why I try to make it as, is it ambiguous? Or as
Generic.
as generic? Yeah. As generic as vanilla as possible.
Vanilla's the generic ice cream. Generic is like.
So let's say we have this. BC bisects angle ABD. Oh, I should write it, sorry. Let me write it as BD so I can do ABC. So if I know that ray BD bisects angle ABC, if I know that happens, I know then I have a diagram that looks like this. I know that these two angles are going to be congruent to one another just from that statement. Which means, what are the two angles that were created that are congruent to one another? Done. That when you would state then, you're given, then you can say angle ABC is congruent, angle CBD. And what do you think the reason is? Definition of an angle bisector. It doesn't, we don't know what that is. I mean, it doesn't matter really. What we're doing here is we're just using this angle bisector. We're using the definition of the angle bisector. I'm not saying whether or not something is obtuse or acute or anything like that, because in how it relates to this generic statement, it has no bearing. Okay. So that's a definition of the angle bisector there. Excuse me. Not so bad so far?
And we could almost even write these as conditionals, couldn't we?
Yes. Every single one of these can be written as a conditional. And that's because if given an angle bisector, then angle congruent to angle. And that's where the whole idea of the logic stuff came from, because that's why we wanted to start you guys with some of the logic to understand the if-then statements of these. That's how this stuff is all done. Okay? Let's see, what's another one that we can do that's pretty simple that I know will show up in the next couple days? How about complementary? That shows up a lot in the next day or two. What do complementary angles do? Good. Two angles who angle measures add up to equal 90. So let's just say we have a statement that's given to us. You have complementary angles. If given, if you're given complementary angles, angle plus angle equals, well, what do complementary add up to equal always? 90. So that means that, and that I like how you said it, angle plus angle equals 90.
90 degrees.
What do you think it would look like if we did supplementary? We're going to do that one next. If you want to start filling that out, we'll try and parallel them at the same time here. So here's our example. Angle A and angle B are complementary, and that's given. So if angle A and angle B are complementary, thank you. What would you say? Done. Perfect. And what do you think your reason is? What are we using though? Definition of complementary. Definition, complementary angles. Notice how I'm abbreviating everything? The way that I abbreviate stuff is the legal way for you guys to abbreviate stuff. Please don't make up your own abbreviations. Yeah. What would a diagram look like for this? Perfect. Two acute angles equal 90. So I know I'm going to have a right angle here. And it doesn't really matter how it looks. I can just say here's angle A and here's angle B. That's it. It's really all you have to do. Their angle, the angle measurements for A and B really don't matter. They really don't. Okay? We can just have it set up like that. So what do you think? What do you think the differences are going to be between this and supplementary? Yeah. This is going to be 180. So let's make the next one here real quick supplementary. Okay. Can I go to a clean one, or do you guys have this down yet?
What up?
Wait up, Mark.
Alright, I got it.
Good. Let's do another one. If given supplementary. Very, very straightforward. If you're given supplementary, we know that angle plus angle equals 180. Which then means that my example, to come up with our proof, angle X and angle Y are supplementary. Bless you. Angle X and angle Y are supplementary to one another. That's given. What would I say? Perfect. Angle X plus angle Y equals 180. And what do you think the reason is? Perfect. Definition, supplementary angles. Have you noticed so far that everything that goes in the reason bank, the reason side there, it's always been a definition? Kind of important to pick up on. You're always using definitions here, guys.
So we're doing all both sides.
Most of it. There's a lot of stuff that we're gonna use, okay? There's a lot of stuff.
For the entire year.
For the next about the first semester. Oh, this reminds me. Do me a favor. Every day that we get out of here, right before you guys leave, I know every one of you guys grabs your phone. Take a picture of your progression sheet every day. Because if you lose it, then at least you have a backup copy of it. Does that make sense? Make sure you take a picture of it, that way you always have a backup of it. I'm telling you to. Okay? And then obviously our diagram. Something like that. Okay. What else creates supplementary angles? No. Starts with an L and ends in a pair. Linear pair. So let's do that one. Linear pair. If given, linear pair. This one mirrors it very, very similarly. If given, linear pair. If you're given that you have a linear pair, the easiest thing to do, I'm trying to think if they use supplementary off this or not. I don't remember if they use supplementary on that one, do they? Do they say it's a supplementary pair of angles, or it calls it create a line?
Yeah, it's two adjacent angles whose non-common sides are opposite rays. I like saying that they're adjacent and supplementary.
Okay. But I'm trying to remember proof-wise if they just go, then they say linear pair. I'm just gonna go right to supplementary. And we'll say if linear pair, then they're supplementary, if they're supplementary, then they do this. Okay. Let's do this. We're gonna do two things. We're gonna create a two-step progression here. Because if we have a linear pair, then you know you have supplementary angles. Then if you have supplementary angles, what do they add up to equal? So we're gonna do this. We're gonna state that you have supplementary angles, and then progress to angle plus angle equals 180. We're going to do a two-stepper here. Okay. Linear pair states that they're adjacent supplementary angles. A lot of times in our proof stuff, there really isn't much that talks about adjacent, but we talk a lot about supplementary. We can do a lot of things with supplementary. You'll see a lot of substitution steps and things like that eventually. So what we're going to do is we're going to create two steps. We use A, B, X, and Y, so let's use C and D. Angle C and angle D are linear pair. And that's given. So if you are given a linear pair, you're going to say two steps. First thing I want you guys to say is that the two angles are supplementary to one another. Okay? Why do you think I should say that? What do you think my reason is going to be? What has been the reason for every one of these so far? Definition of whatever I wrote down here first, right? So what's going to be my definition of what here? Definition of linear pair. And now, since you have on your progression sheet, that just went flying away, you have something on there about supplementary angles. You have supplementary angles, so what are you going to say? No. Reach progression sheet. You have supplementary angles now. What are we going to say? What are you going to say? Perfect. Since I have supplementary, the next thing I would say is angle C plus angle D equals 180. And what's the reason now? What'd you just use? Supplementary, very good. A lot of times you're gonna need those intermediate steps to get to something that's gonna be useful. One of the things that we first use a lot of in working with proofs is we do a lot of substitution steps. But in order for us to do that, we have to get things in terms of addition, terms of multiplication, things like that, because we know how to work with algebra, which I know you guys do because you did really well on those algebra proofs on the quiz. So it's very easy to work with supplementary, complementary, linear pairs, angle bisectors, things like that, because the algebra setup of it doesn't change. It doesn't change from the addition property to quality, subtraction property to quality, things like that. We can still utilize them within these. I guess the best thing to do here is kind of the same idea. I know that this is C and D. They're gonna create a linear pair. They're gonna add up to equal 180 degrees because they form a line. Okay. I think but that's not so much like a given.
Oh, one definition.
Yeah.
Okay.
I'm trying to remember. I think that's all we had right off the bat. And now it's just all that's left is wait for this. It comes up again. We can do second edition. Yeah. Let's throw this one on here. This is not a what does segment addition look like? Taking your notes today again, I'm assuming? Why don't you write your notes though? Because are you writing them on here? What does segment addition look like again, guys? Adding segments. What do they have to be though? In order to add two segments together, what do they have to be? No. Same line, they have to be collinear. First of all, they have to be collinear. So remember, segment addition is segment, bless you, plus segment equals larger segment. And then maybe within that same square, because it didn't take up much space, let's do the same idea with angle addition. In order to have angle addition, what do they have to have in common? No, these are angles. Vertex, very good. In this case, I want to make a note here saying that they have to be collinear. Here they have to have a common vertex. So then basically, angle addition was angle plus angle equals larger angle. Just a little reminder. Shall we try one? All right. Let's see.
Can you go back for 1 second?
What, 7 of them? 8, maybe? Not too bad. We go whiskey?
Yeah.
look at what we can do with a 2-column proof. Now, what I started with you guys here today is that we wanted to make sure that you had a bunch of these progression ideas written out. A lot of the background to these things. Now, whether or not you're going to use it each and every time needs to be seen, because each problem is always a little bit different. Okay. So in this case here, if I see that I have given AC is made up of AB plus AB. Let's walk through what this looks like when we have algebra mixed with geometry. Okay? Let's walk through this one. Let me put this on a clean sheet so we have some space. Okay? Now, when we do proofs, what I'd like you guys to do is draw out your diagram. I want to draw our diagram and write down your given and your proof. What they're asking you to do is to go through some steps to show this. They want you to show via logic that AB equals BC. What you're going to use are going to be a mixture of your progression sheet and or your reason bank. Remember that other sheet with the algebra stuff on there? You might want to have that handy as well, just in case you have to refer to it. Okay? What's that?
Your given should be AB. Right here.
Yeah. Yeah.
Also, then we have to do this.
So, how do you start a proof? What do you do first? The given. Very good. So we write down the given. AC equals AB
Write that in a box.
plus AB. Nope, this is an actual proof. Now, take a look at your diagram. According to your diagram, it shows that AC is made up of what two segments?
A, B, F, B, C.
So, let's write that down. Now, when I'm using something off of a diagram, what did I just use, though, to show that that works? Isn't that just segment addition? Two smaller segments added up to equal the larger? If you look at the diagram, that's what it's made up of. Question? Well, we're not doing that, okay? Because you can use, what you're doing is that we're trying to set it up using logic and reasoning, not just throwing numbers. We don't do it that way. We use it this way. Okay? So what we did here is that we went back, we looked at the diagram, and we used segment addition. Segment addition says two smaller segments add up equal to larger. We have that on our sheet, but it's also something you can use from looking at a diagram. Those 3 points are collinear. It's okay to do. Okay? Now, on your reason bank, we have a property called substitution. Substitution is when two things equal two other things. Those other things are equal. It's kind of weird to think of it that way, but take a look at what you have here. Do you have AC here and here?
Yes.
Does AC equal two different things on the other side?
Yes.
That means those other portions are equal to each other. So here's what happens. You can then say this. AB plus AB is AB plus BC. Because you had that segment, the larger segment, was equal to two different things, written out wise. That means those two other parts have to be the same. Putting in something for something else is substitution. So all we did here was substitution. What do you have to prove? AB equals AC. Well, I have an AB and a BC, and I have an AB and an AB. How do I get rid of the AB from both sides?
Well, it's AB.
Subtraction. If you're subtracting the same thing from both sides, the equal sign, what are you using?
Subtract.
Subtraction, property, equality.
Subtraction.
You're subtracting the same thing from both sides. Instead of using numbers like we did last week, what am I doing? I'm subtracting. Okay? But when you do, what's that? But what happens when you're doing this in terms of geometry, since this is the same thing on both sides, all you have to do is this, because you know that's going to happen. We don't write out this simplified step anymore. We can say this because of sub t prop equal. You can write it out, and you just and when you wrote it out that way, it would be it would be a simplified step because you don't use the word. We don't use when we get to the geometry portion of these types of things. We don't use solve anymore. We only use that for the. That's why I just try to do it this way. Okay. Now I know that we went a lot longer through some of these things than I had thought, but what I'd like you guys to try, and I do believe it is. Let's see if I can find it real quick. On the Chapter 2 tab, it's the 2.6 Practice B. There are 2 questions of fill in the blank. Number 1 and number 2. I'd like you to rewrite this out on a separate sheet of paper, and then you guys have to figure out the reasons that they wrote these things down for those 2 questions. And that's just kind of starting our way through it, okay? 2.6b, questions number 1 and 2. I'll just throw this in here right now.
So,
Okay? I want you to do those 2 on a separate sheet of paper, because obviously I didn't print them out for you, because I don't need to.
2.6b.
Okay? So now, take your phones out. Take a picture of your progression sheet. That way you have it. Just in case you happen to throw it away or accidentally recycle it, or you spill coffee on it, or whatever. Okay? That would be me. Alright? And then we'll continue with these things tomorrow. Don't lose these progression sheets, guys.